This lecture is part of an online undergraduate course on complex analysis and will be about the famous gamma function. So we'll just start by recalling its basic properties. So Euler defined the gamma function by this following integral, and it has the properties that S gamma S is gamma S plus 1, and gamma of 1 is equal to 1, and from this you can see that it more or less generalizes the factorial function up to a change of variable. So n factorial is equal to gamma of n plus 1. Incidentally, this wasn't Euler's first integral defining the gamma function. He actually defined it using n factorial is the integral from 0 to 1 of minus log of x to the n dx. Well, these two integrals are actually equivalent under a change of variable, so they're more or less the same thing. And if the real part of s is greater than 0, this converges to a holomorphic function. And using this functional equation, we can extend it to all complex s, and it has poles at s equals 0, minus 1, minus 2, and so on. And now we should take a look at it and see what its basic properties are. So here's the famous graph of it from Janke and Emder. And this graph is a sort of graph of the absolute value of the gamma function on the complex plane. So this is the real axis and this is the imaginary axis. And there's a huge cliff here. And this cliff is caused by the fact that gamma of n is n minus 1 factorial. So it grows really, really, really fast as you go along here. Then we have the poles at s equals 0, minus 1, minus 2, and so on. And you notice these poles are getting thinner and thinner and thinner, so we'd better explain that. The other obvious feature is that the gamma function is very, very small in this region here and this region here. So when the imaginary part of s gets very large, the gamma function seems to get very small in absolute values, so we need to explain that as well. So first of all, let's take a look at the size of the poles. So at s equals 0, the pole looks like has residue 1 because we have gamma s is equal to 1 over s times gamma s plus 1, and this bit here is approximately 1 when s is 0, so it sort of looks like 1 over s. At s equals minus 1, we compute gamma s minus 1 is 1 over s minus 1 times gamma s. So for s approximately 0, this will be a pole of residue 1, and we have to divide its residue by minus 1. So we find the residue is equal to 1, which was this one here, divided by minus 1. So the minus 1 comes from this minus 1, and the 1 comes from here. At s equals minus 2, it's similar. Gamma s minus 2 is equal to 1 over s minus 2 gamma s minus 1. So the residue gets divided by another factor of minus 2. So the residue is equal to minus 1 coming from there divided by minus 2, which is a half. And for s equals minus 3, it's similar. The residue is minus 1 over 2 times 3. And in general, the residue will be plus or minus 1 over n factorial at s equals minus n. So you can see the residues are rapidly getting very, very much smaller, and that's why the poles are getting very, very thin. So if you look here, these two poles are the same size, very roughly. That's because they both have residue of absolute value 1. Residue is 1 and minus 1 there, and then residue a half, 1/6, 1/24, and you can see that this is causing the poles to get extremely thin. So the next thing to look at is why is gamma s small as the imaginary part of s tends to infinity, plus or minus infinity. Well, let's first of all have a look at the integral for gamma of s. So gamma of s is equal to the integral from 0 to infinity of e to the minus t to the s minus 1 dt. And we can take the absolute value of this, and this is less than or equal to the integral from 0 to infinity of e to the minus t times t to the real part of s minus 1 dt, because this is just the absolute value of t to the s minus 1. And this integral here is just equal to gamma of the real part of s. So we find that gamma of s is at most gamma of the real part of s. So this gets us part of the way. So gamma s is bounded for a is less than or equal to the real part of s is less than or equal to b. Here we take 0 is less than a is less than b. And the reason for this is that the gamma of s is bounded for a less than s, a less than or equal to s less than or equal to b in this region. So we've shown that gamma of s is bounded in these strips, but we haven't yet shown it tends to 0. Well, that's quite easy to do, because now we use the fact that gamma of s is equal to gamma of s plus 1 over s. And this thing here is bounded for a is less than or equal to the real part of s is less than or equal to b. So this thing here is not only bounded, but tends to 0 as the imaginary part of s tends to infinity in this strip, because we're taking something bounded and dividing it by s. And we can sort of continue this. We can say gamma of s is equal to gamma of s plus 2 over s times s plus 1, and this says that it's not only tends to 0, but tends to 0 faster than a second degree polynomial. And we can obviously continue like this, and we see that if we take the imaginary part of s to the power of any integer times gamma of s, this is bounded. So here we take n to be any positive integer, and we take a less than or equal to the real part of s less than or equal to b, where a and b are any real numbers. Now you notice you've got to be a little bit careful when s is actually a negative integer or 0, because then gamma of s isn't bounded, it actually has a pole. And that's why we've put this condition n greater than 0 here, because if n is greater than 0, then the imaginary part of s vanishes, so we don't need to worry about the poles. So you see gamma of s is rapidly decreasing in vertical strips. A less than or equal to real part of s is less than or equal to b. So a picture of it looks something like the following. So here we've got the plane, and if we take any vertical strip, so we might take a point A and a point B here, then it's rapidly decreasing, and it's also rapidly decreasing as you go there. And it's bounded except that you've got these poles at various points 0, minus 1, minus 2. So if you cut out a little circle around each pole of some small radius, then gamma of s will actually be bounded in these strips with these little poles around with these little circles around the poles removed. So by rapidly decreasing, it means if you multiply it by any polynomial, then it's still bounded. So it's really decreasing very fast. So next we have a very nice formula for the gamma function, which is probably the most useful formula for it, which says that gamma of s times gamma 1 minus s is equal to pi over sine pi s. And I'm going to give you two proofs of this, a lazy proof and a complicated proof. So let's start off with the lazy proof. So here we have a function, let's call this f of s, and we want to identify it, and we just sort of think of some properties of this. First of all, we notice that f of s is equal to minus f of s plus 1. And that follows from the functional equation for gamma of s. So gamma of s plus 1 is equal to s times gamma s. And if you insert that into here, you find it satisfies this simple functional equation. Secondly, f has a pole of residue 1 at s equals 0. Well, that's kind of obvious. This is a pole of residue 1 and this is 1 there. And thirdly, you notice that it's rapidly decreasing in vertical strips. So here we take a is less than or equal to the real part of s is less than or equal to b, and we want s not too close to one of the poles, so we might take the imaginary part of s is greater than epsilon or something. So it's going to be rapidly decreasing in all these strips, and that's all we need to know about this function on the left-hand side, because you notice the same is true for pi over sine pi s. Again, this follows immediately from properties of the sine function, and the pole at 1 is kind of obvious, and it's rapidly decreasing in vertical strips because sine is rapidly increasing in vertical strips. So we see that gamma s times gamma 1 minus s minus pi sine pi s satisfies g of s plus 1 equals g of s, and it's rapidly decreasing in vertical strips, and it has no poles. It's holomorphic everywhere, because these two have the same poles at all points, so their difference is bounded near all these possible singularities, and therefore you remember that a function that's bounded near a singularity is really holomorphic. So this function is holomorphic everywhere. It's also bounded because if it's bounded in vertical strips, which it certainly is because it's rapidly decreasing, and it's periodic, these two together show that it's bounded. Well, if it's bounded, it's constant by Liouville, because Liouville's theorem says that any holomorphic function on the whole plane is bounded, and any holomorphic bounded function on the whole plane is constant, and the constant must be 0 because both sides are rapidly decreasing. So we've seen this function is equal to 0, and you notice this proof is kind of some sort of black magic. We've hardly we haven't written down formulas for these functions and then tried to calculate them. We've just sort of meditated upon the essential properties of these functions. It suddenly becomes obvious they're equal because they've got the same poles and the same functional equation and the same behaviour at infinity. By the way, we can give a brute force proof of this. This is the hard proof, and I'll just give it so that you appreciate the easy proof. So let's try and do it by brute force. So what I'm going to do is I'm going to take gamma of s times gamma 1 minus s, and I'm going to write it out in the definition. So that's the integral from 0 to infinity of e to the minus t, t to the s minus 1 dt, and then I want gamma of 1 minus s, which is the integral from 0 to infinity of e to the minus u times u to the 1 minus s minus 1 dt. And I can then write this as a double integral, so it's going to be a double integral of e to the minus t plus u times, well, here we've got a t over u to the power of s, and we've got a dt over t and a du there. So this is, we're doing a double plane integral. And I'm going to change variables. I'm going to change t to t times u, and this gives us a double integral of e to the minus ut plus u times t to the s times dt over t times du. And now we can carry out the integral over u, so this now becomes the integral. Well, the integral over u is easy. That's just going to give us 1 over 1 plus t, so that's 1 over t plus 1, t to the s dt over t. And now this integral is one that I sort of left as an exercise on one of the earlier Bromwich contour problems, and it's just pi over sine pi s. So, okay, we can do it without using the elegant thing, but it's quite a mess. You know, we need to do a double integral, a change of variable, and then we need to, at the end, we need to do this contour integral, so we need 3 or 4 steps to do it. So it's much easier to do it just by using Liouville's theorem. Incidentally, there's nothing wrong with this brute force method approach, because this brute force method does actually generalize very nicely to various high dimensional integrals. I mean, you get extensions of this turning up when you try to evaluate Feynman integrals in quantum field theory and so on. this sort of illustrates a theme that Riemann had, which is that in order to study a function, a complex function, you should focus on its singularities and its growth rate. And quite often a function can be characterized by its singularities and growth rate. Incidentally, there are a couple of useful properties of gamma s times gamma 1 minus s equals pi over sine pi s that we ought to note. First of all, let's put s equals a half. Well, we find gamma of a half squared is equal to pi over 1, so gamma of a half is equal to root pi. And again, if you look at the integral for gamma of a half, it's the integral of 0 to infinity of e to the minus t to the minus a half dt, and it's not at all easy to work out this integral directly. If you change variable, it turns out to be the famous a constant times the famous integral e to the minus y squared dy, which is kind of a bit tricky to do. The other application is that gamma of s is never 0. This follows because pi over sine pi s is never 0, so gamma of s could only be 0 at points where gamma of 1 minus s has a pole, and gamma of 1 minus s has a pole only at s equals 1, 2, 3, 4, and so on, and gamma of s is obviously not 0 at these because it's a factorial. So gamma of s actually has no zeros at all. Next, we can find a nice characterization of gamma s. So gamma s is the only meromorphic function such that, first of all, we want s gamma s is equal to gamma s plus 1. So this is the function equation of the factorial function. So if we want to generalize factorials, we'd better have an equation like this. Secondly, it's bounded in strips of the form a is less than or equal to the real part of s is less than or equal to b, provided the imaginary part of s is greater than or equal to 1, say, because we've got to stay away from the poles, of course. It's very annoying having to put this condition in all the time, but whatever. And the third property is that gamma 1 is equal to 1. So this is obviously just a normalization. Because we could, if we had any function with these two properties, we could just multiply it by a constant and it would still have these properties. And proof, it's very easy. Suppose gamma naught has these properties. Then gamma naught of s times gamma of 1 minus s is equal to pi over sine pi s. And the reason for this is that our proof of this for the gamma function works just as well for if we replace the first bit by any function with these properties. And since gamma of s times gamma 1 minus s is equal to pi over sine pi s, we see that gamma naught must actually be equal to gamma. What this does is it shows that gamma of s is in some sense the smallest generalization of the factorial function. I mean, any generalization has to satisfy conditions 1 and 3, and anything that doesn't satisfy 2 has to have rather high growth rate in these strips, whereas gamma of s not only has low growth rate, in fact tends to 0 very rapidly. I mean, of course, we can find lots of other functions that satisfy this property. We can just multiply gamma by any function with period 1, and it will still satisfy this equation. So there are huge numbers of functions that aren't bounded in vertical strips, but gamma of s is the smallest possibility. Well, how can we use this characterization? Well, we can use it to prove lots of other equations for the gamma function. So I'll give one example here. Suppose we look at the function gamma of s over 2 times gamma of s plus 1 over 2 and think about it a bit. And you remember, whenever you see a holomorphic function, or meromorphic function, you should think about its growth rate and its poles. Well, this is poles at s equals 0, 2, 4, and so on. And this is poles at s equals 1, sorry, minus 2, minus 4, minus 1, minus 3, minus 5, and so on. So if you put these together, this has the same poles as gamma, or at least they're in the same place. So this suggests that this function has something to do with gamma, and let's try and figure it out. Well, first of all, let's look at the function equation. F of s plus 1 is equal to gamma of s plus 1 over 2 times gamma of s over 2 plus 1, which is equal to s over 2 times gamma of s plus 1 over 2 gamma s over 2, which is equal to s over 2 f of s. Okay, well, this is almost the equation for gamma of s, except we've got this stray factor of 2 here. Well, that's not very difficult to get rid of. Now let's look at 2 to the s times gamma of s over 2 times gamma of s plus 1 over 2. So if you put g of s equals this, then it satisfies g of s plus 1 is equal to s times g of s. So it's the same functional equation as for gamma. What about its behaviour in vertical strips? Well, it's obviously bounded in vertical strips, except near poles, because this is true for gamma of s, and 2 to the s is also bounded in vertical strips. So g of s is equal to some constant times gamma of s, because gamma of s is a unique function with these properties up to a constant. And what is this constant? Well, let's put s equals 1. So we have 2 to the 1 times gamma of a half times gamma of 1 is equal to the constant times gamma of 1, and gamma of 1 is just 1. So 2 times gamma of a half, which is root pi, times gamma of 1, which is 1, is equal to this constant. So the constant is 2 root pi. So we find that this is equal to 2 root pi times gamma of s. So this is the famous duplication formula for the gamma function. You remember when we discussed the Riemann-Zeta function, I first proved one functional equation for the Riemann-Zeta function, and then gave a sort of neater one in terms of pi to the minus s over 2 gamma s over 2 times zeta of s. Well, in order to prove the equivalence between these two functional equations, you need to use this duplication formula for the gamma function. So I guess you can leave that as an exercise if you want something to do. So I'll end with another problem. So here, instead of having a duplication formula for the gamma function, we can extend it. So let's look at m to the s times gamma of s over m, gamma of s plus 1 over m, all the way up to gamma of s plus m minus 1 over m. So the problem is to prove that this is equal to 2 pi to the m minus 1 over 2 times the square root of m times gamma of s. So this is, I think it may be due to Gauss or something. So what you do for this is we copy the proof that I gave for m equals 2, and the only problem is to work out this what exactly this constant is. And to work out the constant, one way of doing it is to use the fact that gamma of s times gamma of 1 minus s is equal to pi over sine pi s. And using this formula and a little bit of algebra or whatever, you should be able to work out this constant. Okay, that'll be enough for the gamma function for the moment, although I'll probably come back to it in a later lecture because there's plenty more to say about it.